session. So for the first talk, we're very happy to have Molei. Molei is a professor at Georgia Tech. He works on all types of things like in sampling, diffusion models, optimization, applied math more generally. Today he's going to tell us a little bit about creativity and test scaling methods for diffusion models.
All right, thank you very much. Thank you all for being here. This is a really nicely put up workshop. So I'm trying really hard. I'm squeezing 2 talks into one because it's a rare situation to have such an amazing audience. So hopefully I don't go over time too much. So part 1 of this talk is about creativity of diffusion model, and this is a joint work with my former postdoc Yehe, who is currently at CU Boulder, former undergraduate student Yitong. And it's a paper that was recently published in ICML workshop. So the goal is to quantify what kind of creativity does continuous diffusion model have. And the reason is, for example, so there are a lot of people interested in like AI for math. People always debate about whether like AI can create new proof techniques or it just knows every single proof technique existent on this planet. And I don't really have an answer to this question, but I have an answer to some more modest question, which is that when a diffusion model generates new samples, what kind of new samples does it generate? So I don't think this audience needs much introduction to diffusion model. So the forward process basically transports data distribution to noise, for example, Gaussian in this situation. And as you gradually add noise to the data, you also learn a score function which sort of characterizes how the entire data density evolves forward in time, which is helpful because then you're trying to do something that is illegal, which is you start with pure noise and then you invert the time of the forward process so that structure gradually emerges, and then you get IAD sample from the data distribution. And of course, all of you know that you do that with the aid of the score function, so you can make this very mathematically rigorous. I'm not going to say too much about this given this expert audience, but just one thing that the score function is actually learned during the forward process. So it's not really like an oracle that you can assume it's done via some optimization process. So for example, you minimize the denoising score matching training objective with respect to the parameterization of the neural network that parameterizes the score function. If you do that well, and then also you simulate the backward process numerically to some accuracy, and you can generate high quality content, for example, like this one. But actually people said, wait a second, that seems to be high quality content, but in fact there's a datum in the training set that looks almost identical. So this is a serious issue known as memorization. So you can have generative model that seems to be outputting excellent content, but if it's memorizing, it's actually like a stochastic parrot. It only actually repeats randomly what it is taught. So in some sense, actually in any sense, this is overfitting, but overfitting in the infinite dimensional space of probability measures. So because the goal of ours is to characterize how diffusion model create new knowledge, of course, I should first understand when are generated samples just in the training set. So this can actually happen through a very principled mechanism. The reason is because, of course, you want to be minimizing some kind of score matching objective, but you don't really have the population. So that's why you have to replace this population average by some empirical average over the data samples. And therefore, effectively, the initial distribution of your forward process is actually the empirical distribution. It's like a sum of Diracs. It's not really the population distribution. So if you try really hard, your reverse dynamics exactly recovers the forward dynamics in the sense of probability. And then at the end of the inference process, your generative distribution is distributed according to x0, which is the empirical distribution. So therefore, you will just be sampling from the training set. You're not going to be creating any new information. So this is when memorization actually happens. And this does happen. I mean, if you do everything with infinite precision, for example, in this toy example, I started with just the 3 samples. So 3 Diracs summed up together. The forward process actually pushes everything to Gaussian. The backward process pulls everything back to the same sum of Diracs. And then you're in trouble. You just uniformly sample from the 3 points. So there are actually a lot of very interesting observations that people made. For example, Zara and collaborators, who I hope Zara is in the audience, had this best paper at iClear 24 that said many things, and also other people said similar things as well, which is, well, one of them is, okay, so if you fix the size of the score network in your diffusion model, and then you vary the size of the training set, if the training set is very small, your diffusion model will be memorizing the training set. But as you keep on increasing the training set, the size of the training set, eventually your diffusion model is generalizing. There is no more memorization. If you think about it, okay, so memorization requires perfect score, but what is perfect score? The perfect score is associated with this singular object, this like irregular density, which is not even a function. So in practice, you use a neural network which has some regularity. So you are actually approximating something irregular by something regular. So as a consequence, you get like a smoothed version, for example. Maybe you get density like this. So regions that are actually highlighted in yellow correspond to regions that are created by the sort of like the approximation error of the neural network. So you suddenly start to have densities outside the training data set. Okay, so this is one reason where you can one situation where you can have generalization. And now if you think about this picture, okay, you fix the neural network size. So if the training set is very small, your neural network is very strong. So you can actually well approximate the score function. So you actually get like very narrow yellow area. So you get memorization. But as you keep on increasing the training set size, you start to have more and more Diracs, and then your neural network of fixed capacity is no longer to approximate everything very accurately. So you get inaccurate approximation, and then you start to generalize. Okay, so this is the thinking that a lot of people have. Nowadays, you can make it even very quantitative. But one thing that I want to mention is that I only talked about score error. There are other sources of errors, like integration error, initialization error, early stopping, etc. So all of them actually can contribute to the generalization of diffusion model. So yes. Yeah, so good question. So sticking to just the strict diffusion paradigm. So ideally, you want to run the forward process forever so that you get to Gaussian. But you can't really do that. So you run to capital T, where capital T is very large, and then you do the backward process. But you can't really initialize the backward process using like the distribution at capital T time. You don't know what the distribution is, so you initialize at Gaussian. So there's a small discrepancy that actually gets propagated through the nonlinear dynamics of the backward process. Yeah, good question. Thank you. So the question is, do we have a general theory that is also explicit and quantitative? So the answer is yes, but in a non-trivial way. So in the literature, there are already a lot of generalization results. For example, this is a result that I liked because we did it. It even analyzed the training dynamics of the score function and combined the analysis with the inference analysis. So in this bound, you are really comparing like the population distribution of the data with a generated distribution, which is based on like the empirical training set. So this Q is the empirical distribution. This P is a population distribution. So this is why this is already a generalization bound in the sense of a classical statistical learning. And in fact, there are a lot of such results. For example, there was a relatively recent paper that actually improved the generalization part of this result, even though there is no analysis of the training at all. There are a lot of experts in this audience that focused on like the generation accuracy part of the result as well. Highly non-trivial results. If you don't know, I highly recommend. But what we want to do is something better. What do I mean by that? So first of all, generalization bounds like this are intrinsically loose. What do I mean by that? Okay, so in practice, you are only given like a finite training set, so you have empirical distribution. Of course, the belief is, okay, so as the sample size goes to infinity, there is some underlying population distribution. However, you never have access to it. So all you have is the empirical distribution with some data size. And then you start to say things about the population distribution. So the population distribution has to be consistent with your empirical distribution. So it's somewhere in this blurred ball. And therefore, whatever you say has to account for the worst case. So that's why, like intrinsically, your assessment has to be loose. But if you think about, for example, generative AI or diffusion model in particular, it just feeds on this empirical distribution, and then it spits out something very concrete, like this yellow thing. So that's why we don't really want to say how this yellow thing relates to the population distribution, because the population distribution can be anywhere. You don't really have it. So we want to directly quantify the difference between this yellow thing and also the empirical distribution. So this is why and how we can quantify creativity. And also, a bound like this is just a bound. You get a value. It's not really explicit. It's an overall quantification of the difference, but what we want is some sample level result. What I mean by that, for example, this is a beautiful paper empirical paper produced by the Carnegie Mellon group. So on the left is just 25 points, roughly speaking, in 2D. So that's a training set, and on the right is what you would have generated if you train a good diffusion model. So each blue dot here is a generated sample. So you can see the generated samples actually follow some very delicate geometric structure. You don't really have things inside those small boxes, nothing along the diagonal. You don't have overshooting outside the bigger box either. So we want to know, like, where are those blue dots? Of course, this is beyond what a bound can explain. Of course, there are people who say, oh, this is pretty trivial. This is just mode interpolation. You take the closest 2 points in the training data set, you connect a straight line, and then you get your generalization. First of all, this cannot be right. Why? So suppose your training data is in 1 million dimension, and then does generalization only happen in 1D? Second, it's not really a straight line. For example, we ran experiments. This is a toy case where I only have a training set of 3 points: this cross, and this cross. And then the generated points actually follow some curved structure. So it's not exactly like just a piecewise linear interpolation. So the main contribution of this part is a theory that can actually explain this. So very roughly speaking, the conclusion is that generalization happens around something called log density ridge, which is a notion that we introduced. You're not supposed to be staring at this. It should be more intuitive than this. For example, so if you think your probability density as a landscape, and then what would be the thing that you care the most about? Of course, the local maxima, right? So you have one here, maybe one here as well. What would be the second most important thing that you care about? It would be the ridge, literally the ridge that connects those local maxima. So this log density ridge set is actually a multi-dimensional generalization. So it's the literal ridge is 1D, but this definition actually works in multi-D. Roughly speaking, you look for like D-star dimensional structures that sort of are locally high along this structure, but if you go off the structure, you have like very, very steep drops. So what I want to emphasize is that log density set is actually defined by the empirical distribution. It's defined by the finite training set. For example, here I think I have like 13 points, and then you can define a ridge. And so this is a finite sample situation. Of course, if you're a statistician, as the number of samples goes to infinity, the corresponding ridge would actually converge to what people typically assume, like the population distribution is supported on some low-dimensional manifold, etc. So you can actually recover the population limit. But what is important is that we are no longer assuming anything. We're not assuming like low-dimensional structure or anything. You actually construct the low-dimensional structure in some sense from the training set, from the finite training set. Sure. Yes.
What's wrong with the intuition that the high likelihood points are not where the probability mass is? Is it because the region is low dimensional? Because the likely
Yeah, great question. So I haven't, it'll come up very shortly, but in short, okay, so the theory says that the generated points are concentrated on the ridge, or really around the ridge, but it doesn't say like where they are on the ridge. I haven't talked about that yet. So it could actually, for example, the training sets are actually on the ridge. So if you have memorization, and then you just have like a singular distribution on the ridge, but it's still on the ridge. Yes?
Is this theory completely architecture agnostic? Like, is it?
Great question. So you will see. So what I talked about so far is architectural agnostic, as long as your approximation is accurate enough. I'll talk about the nuances, just important difference created by architectures just in a second. Thank you. Right. Okay. So, but the version that I gave was 2 cores, as already shown by the excellent questions. So, so the still short version of the theory is like this. Okay. So you have your empirical distribution. That x0 follows, and then the forward process actually creates a time-dependent family of distributions, but all dependent just on the training set. So for each one of them, so this pxt, there is actually going to be an associated ridge. So there is actually a family, a time-indexed family of ridges, and this family is going to be important. So in practice, you're never going to be just using the exact backward dynamics, because if you do everything exactly, then you just have memorization. So you actually use a neural network approximation of the score, for example, and you want to relate this y tilde to this this time-dependent ridge. So the theory works like this. So initially, your y tilde is distributed according to Gaussian. So there is some ridge which is irrelevant at this moment. And then as time goes on, your distribution of y tilde actually gets attracted to the time-changing ridge. Once you are close enough, you enter a second phase where you have some probably exponential contraction in the normal direction to the ridge. And at the same time, you start to have a sliding motion where you also have like tangential movement of particles along the ridge manifold. And what kind of distribution that you get along the ridge manifold is actually specific to the training dynamics as well as the architecture. We can actually make it very explicit in certain situations, but not in all situations. I'm not gonna say too much about the technicalities, which are interesting, but the main message to go is that this theory sort of characterizes the inductive bias, which leads to the creativity of diffusion model, and it's layered. So there's there's an outer layer. So in this outer layer, you basically just have the inductive bias of the inference dynamics, which actually gives you the geometry of the ridge. So at this moment, this is actually agnostic to the training and also the architecture. Of course, you can't be like completely off. It has to be accurate enough. But then there's an inner layer which corresponds to the fine distribution that you achieve along the ridge. So this is actually specific to the training dynamics and the architecture. Like I mentioned before, so if you have perfect training, perfect infinitely capable architecture, then you just recover the sum of Diracs on the ridge. Okay, so it of course can explain the curves that I showed earlier, and also it works in high dimensions as well. I'm not going to say much about this. So if there's no additional comment or question, I'm going to change switch gear and talk about test time scaling of discrete diffusion model. And this is a joint work with my student Ki Chong and also Jun, who's in the audience. So the big picture is the following. So given a pre-trained model, how do we make it better? So this is a plot produced by NVIDIA. So it's a common paradigm. So the x-axis is the number of computes. The y-axis is really like the performance. So I mean, if you want to like get money from VC, you say intelligence. You first start with like scaling the pre-training, and then you scale the post-training, and then finally you scale the you do test time scaling. So just in case those terminologies are too fancy, so in post-training you typically do things that are like fine-tuning. So you first do SFT, and then you do like reinforcement learning fine-tuning. But in test time scaling, you have a lot of different approaches. For example, best of n is one of the popular test time scaling methods. So the difference between these two phases is that in test time scaling, you're not really changing the weight. You probably don't even have the weights of the model, but in post-training, you will change the weight. So this paradigm actually worked out very well for autoregressive large language model, and there are people like me who try to make it work really well for diffusion models as well. So in this talk, I'll just be focusing on a diffusion model, and in particular discrete diffusion model and its test time scaling. So yesterday, Yongxin actually gave a very nice talk about reinforcement learning fine-tuning of a continuous diffusion model. But the stuff that we do together actually work for discrete diffusion as well. But still, let's just focus on test time scaling. But interestingly, the goal is actually shared between test time scaling and also post-training, fine-tuning post-training. So the goal is, okay, so you have a pre-trained model that samples from some measure, pi ref. You want to make it better actually in a very specific way specified by a reward. So this reward is something that is usually given to you, and then you want to sample from a tilted distribution where you multiply these two things. What is tau more precisely? So for instance, you can have a hard constraint where this tau is like a verifier, so it's a 0, 1 valued. For instance, if you care about like math, if like a math expression 1 + 1 is equal to 3 will not satisfy the constraint. It's a wrong expression. You don't want to generate it. Some expressions are correct. Some expressions are hard, but for example, nowadays known to be wrong. For example, if somebody shows you a proof of Jacobian conjecture in 3D, you know it's wrong nowadays. It doesn't have to be math. If you don't like math, you probably shouldn't be here. But Sudoku is not really better. But if you want to solve a Sudoku, if the Sudoku satisfies the constraints and it passes a verifier, so you want to only be sampling, those configurations that satisfy those hard constraints. But the constraints don't have to be hard. It can be soft. For example, it can be a reward, continuously valued reward. For instance, if you're generating molecules for drug design, there are a lot of metrics like quantitative estimate of drug likeness score, etc. So these are continuous valued functions. And of course, by incorporating this reward into the tilted distribution, you're encouraging like high reward generations. So what are common test time scaling methods? For example, best of n is very popular, and in fact, it's popular for good reason. It's actually very hard to beat, not only empirically, but also there are theoretical reasons. What is best of n? So you draw n samples from the reference measure, and then you just keep those with the highest reward values. So it's very simple, but it's really like a test time scaling method. So if you make n bigger and then you spend more compute, then you get better performance. So if your verifier is actually like for hard constraint and then conditioned on that you actually have some success, so at least one sample actually satisfies the constraint, best of n actually samples the constraint distribution correctly. But it's not always the case. So for example, if you have this like soft constraint situation, continuous reward, best of n actually messes up your tilted distribution. So it's not really sampling from the tilted distribution. But people use it anyway. They typically only care about high reward outputs, and then that's fine. So that was some background of my, really just like introduction to my notations. And I should have clarified, if not already, that our context from here on is going to be discrete diffusion model. So it's discrete in the sense that the datum is discrete, or more precisely, so we will be dealing with sequences of tokens, and each token will be from some finite vocabulary. So well, unless you just came out of a cave, you know that autoregressive large language models are very good at generative modeling such sequences. But that's not the only choice. For example, you can have diffusion language models that do that as well. There are actually multiple types of diffusion language models. For example, you can actually have uniform diffusion, which is like, okay, so you design some forward process such that it actually pushes forward the data distribution to uniform on each token. So this should be, of course, be contrasted with the canonical continuous diffusion model, which pushes forward the data distribution to Gaussian. But of course, you don't really have Gaussian in discrete state space. But you can do other things as well. You can have masked diffusion, where you actually introduce an additional token, artificial token, which is a mask token, into the vocabulary, and then you design some forward process that just gradually masks tokens, and eventually whatever data distribution you have would be actually pushed forward to a Dirac peaked at an all masked state. And then in the backward process, you again just try to invert the time of the forward process. So you randomly pick locations, and then you unmask the masked tokens at those locations into real tokens, according to, of course, some learned probability. Okay, so this is masked diffusion, and there are more, but this talk will actually be focusing on masked diffusion from here on. So here's some illustration. So on the left, it's an autoregressive model, so you are just doing next token prediction, according to some probability that you learned that is based on all the previous tokens. So as Jerry mentioned, for example, this is intrinsically sequential. So you have to always wait for the previous tokens to generate. On the right is an illustration of the inference process of masked diffusion model. So you basically pick like random locations and you unmask. Of course, again, according to some learned probability. So in some sense, what you have here is still like related to autoregressive, and in fact, people say it's Any-Order AutoRegressive in the following sense. Okay, so essentially you can generate in any order. It's just different orders have different probabilities, but conditioned on an order that you pick, you still generate sequentially. So that's why they say it's Any-Order AutoRegressive. And one good thing that people often say is, what are the benefits of masked diffusion model? So one good thing that people say is that if you allow some approximation, then you can do like parallel decoding. You can actually generate multiple tokens at the same time, and therefore your inference is fast. Also, some people believe, okay, so Any-Order AutoRegressive is autoregressive is a strict subset of Any-Order AutoRegressive because it just corresponds to a specific order. So that order from left to right has probability 1. Other orders have probability 0. So therefore, any-order autoregressive is the strictest bigger set, and therefore it should have bigger potential. But there are a lot of nuances. So for example, people say this flexibility is also a trap. So happy to discuss more. But there are a lot of interesting things that people are still exploring. There's one more thing that is actually the purpose of the rest of my talk. So hopefully I can explain that well. But I want to say a bit more about parallel decoding first. So parallel decoding is really a double-edged sword. So it actually makes the speed fast, but you actually compromise accuracy. So this is a beautiful illustration that I borrowed from a beautiful paper, re-MDM by Volo's group. Unfortunately, I don't think he's here. For example, in this illustration, so at some point, you get a partial sequence, which is mask, mask, C shells. And then at some point, you decide to unmask both tokens simultaneously, and then you get she, cell, C shells. So that looks nice, but in fact, the subject is singular, so the verb should really be cells instead of cell. But the thing is, because these two are simultaneously unmasked, you can't really tell. Okay, you cannot get like a cell, cells instead of cell. So the trick that they introduced is, you can introduce this additional operation of remasking. You can remask like bad tokens, and then later on it gets unmasked again, and then you get something correct. Okay, so naturally, this is a test time scaling approach. So the more compute you're willing to put in, the better the sample quality you can get. However, their original approach has no reward, so it's not really sampling from a tilted distribution. And in fact, the derivation is intuitive, very beautiful, but it's not rigorous at that time, so it's unclear like what is exactly the generative distribution or the computational complexity associated with it. There are, of course, a lot of other results. So many useful heuristics. You can do test time scaling using other approaches. Even though this is unpublished, it seems that there is a way to incorporate reward, etc. And also, Satan and collaborators had this very interesting paper where you learn the remasking schedule. So I would roughly say like that this work is between fine-tuning and test time scaling. Highly recommend. But the rest of the talk will just be focusing on remasking. So in fact, related to remasking is a notion called backtracking, which was a recent technique used in autoregressive language model. So here's an illustration that Cloud helped me produce. So suppose you give a language model a prompt. A rectangle has parameter 20 and area 24. Find its dimensions. And then the language model formalizes everything. And then it tries L equals to 8, W is equal to 2, and then check the area. And then there's a problem. Depending on what kind of language you have, you may actually run into different situations. Maybe like a lousy language model will say, okay, 8 times 2 is 24. So it commits an error. A better language model would actually do like backtracking. So it would say, oh, that's 16, not 24. There's a problem. So let me try again. Let's try L equals 6 and W equals 4. Okay, so if you can do backtracking, you can actually do things better. So that's one of the many reasons why I like this beautiful paper, seminal paper. So I believe multiple authors are in the audience. And this paper generalized Sinclair Jerrum random walk to actually develop some principled method for doing backtracking. And also pleasant performance guarantee was provided. So I will abbreviate the method as AR-VGB, where VGB stands for value-guided backtracking. So this is something that I'll actually refer to later on as well. So we have AR-VGB grid method. What about this work? So what did I do? Or what did we do? So we actually do backtracking for diffusion language model on the other, instead of autoregressive. And we do that via some principled way of doing remasking. And then you may say, oh, this guy is just trying to publish paper. Like why do you take an existing method and then just like transplant it to something else? I think I can do, I'm better than that. So what we care about is the computational cost. And you will see, so in fact, here is a simple illustration. So it's a miniature coding problem. So it's a very good problem from TCS called diagrammer, where I'm just trying to generate a sequence of parentheses that is grammarly correct. But here you see it's not. So you have a wrong token. Suppose you generate till the 6th token, and then you realize there was a previous mistake. And then if you use an autoregressive model, somehow you fix this mistake, and then you have to generate again sequentially. So like everything after it is basically like masked. So you have to do things. You have to redo everything, and that could be computationally costly because AR is really sequential. So you do things locally. On the other hand, if you use like a mask diffusion model, it's any order. So you can just mask this token. And then later on, you unmask this token, and that's it. So you actually are allowing global editing. So you can do global backtracking, and therefore things become more efficient. So that's a rough idea, but of course, I want to do better than that. So in order to be more precise, so I have to introduce some backgrounds. So there's a key ingredient called process verifier. So remember, the goal of test time scaling is, given a prompt, you want to sample from some tilted distribution. So the tilted distribution is created by this tau function, which I will call terminal or outcome verifier from here on. And Y in our setup is like a sequence. And when you deal with sequence, you have to be careful. For example, so here is an example: 5-minute meal recipe. Step 1: make the dough and let it rest for an hour. So I followed it, and then I realized that I became really hungry. You don't really have to wait till step 16 to say, oh, this is a bad generation, right? So it's wasteful not to verify before completion. So that's why people actually were thinking about process verifier. For example, one approach to do process verifier is via Monte Carlo rollouts. So the idea is very simple. So suppose you have Z or Z, which I denote by like incomplete sentences. Suppose you just generated a couple of tokens. And then what you can do is you enumerate all possible completions of this incomplete sequence, and then you average their like outcome values. Okay, so this would be an ideal process verifier. Of course, you don't always have it analytically available in practice, so you often actually learn it, and that's a problem. So if you have error in the process verifier, it actually makes the test time scaling non-trivial. So in fact, so here is an algorithm that was not invented by me, but I just for simplicity call it value-guided rollout. Which actually works if you have the perfect process verifier. So what it does is, okay, suppose you have a partial sequence Z. What you're trying to do is, so you try to move to a new state, a new sequence with some probability. So if the probability of moving to a new sequence with the J's token unmasked to a value A is given by a product. What is this product? So first of all, you use a reference measure, but this is actually the value of the reference measure at a completed sequence that has the J's token being A, and also this completed sequence has to be agreeing with the partial sequence in terms of what have already been generated, and also there's a prompt. Okay, so this is the first term, and then there is a second term. This second term is basically like the second term is basically like the partial value of the proposed move of this new with the J's token being A. Okay, so this is actually a forward-only process. Okay, you only just keep on unmasking. There's no backtracking. If your verifier is actually the exact process verifier, it does sample from the tilted distribution. But in practice, it doesn't. And in fact, it's very bad. The error actually compounds. If your learned verifier has some error that is multiplicative, so some bounded error from the ground truth verifier, and then the error of like a length L sequence could actually be exponential in L. This is extensively discussed in the seminal paper. Again, it's not done by us, but this is for illustrating why what you want to do is to have an inference algorithm that actually converges to the tilted distribution that effectively utilizes the process verifier and also importantly is robust to the verifier's error. Okay, so our result is called AOAR-VGB, so it's the mask diffusion version of VGB. But also I want to be very fair. So AR-VGB can actually accomplish these goals as well. It's just the AOAR-VGB is a little different, and I've talked about some of the differences, and now I'll talk more. The setup recapitulated. So X is a prompt, Y is a full sequence, Z is a partial sequence. You want to sample from the tilted distribution. You want to use the ideal process verifier, but you don't have it. You only have practical approximated verifier V hat. And AOAR-VGB actually is a Markov chain with carefully designed transition probability. So at a current state Z, incomplete sequence, you can do two things. Either you can unmask, so it's a forward step, or you can do backtracking by remasking. So here B is like a collection of indices. Just in case you know things like block diffusion, like this B is like a block of tokens. So here the proposal is like you take a couple of a collection of indices and then you unmask those tokens into like values given by a set AB. And you actually do that transition according to some carefully designed probability. And then you also allow remasking. So given a partial sequence, you can actually remask certain tokens, again described by this set B, according to some probability. So the expressions are a little complicated, but if lambda is equal to 0, and also you don't do any remasking, and then you actually recover like this forward-only process that I mentioned earlier, that does not work unless you don't have error. So really, it was this backtracking step that actually helps correcting the error. I'm not going to say much about the technical things, but essentially what you have here is a stochastic greedy algorithm inspired by Sinclair Jerrum and also AR-VGB. You basically unmask promising blocks, and also you remask suspicious blocks. Even though it's a greedy algorithm, you do have guarantee. So the guarantee actually is pretty nice under mild conditions. So as long as your learned verifier is like bounded in this multiplicative sense, and also your learned verifier at complete sequence would actually return like the terminal verifier's value, and then it works. Z is incomplete sequence. So what is this curly Y? I forgot to mention. So it's like the collection of leaves. So suddenly, like, what are leaves? So for example, if you think about autoregressive model, you could think like doing a random walk on a tree. So the number of unmasked tokens would be like the depth of the tree. So you start at the root, so nothing generated, and then you go down to the leaf. If you allow like backtracking, in the AR situation, you actually have to go back to your parent node, and then you can do something else. But in AOAR-VGB, you're not really following a tree. You're actually doing a random walk on a graph. The reason is because, so you, for example, generate one more token, and then you realize something is wrong previously. You can actually unmask that token, so you actually go to a different node. You're not really just going back to the previous step. So if you sort, for example, the leaves according to the reward values, you feel like you can actually go to the right quicker. So some more quantitative versions of the theoretical guarantee So first of all, the method is asymptotically unbiased, and so the stationary distribution at leaves is actually the tilted distribution. I want to just to finish, maybe 2 more minutes, 2 or 3 more minutes. Also, you actually get fast mixing, so you actually reach the target distribution relatively quickly under some situations, and also you actually hit the leaf node relatively quickly. So what I want to emphasize is the fact that here this L dependence is actually quadratic in both results, where L is actually the length of the sequence. And this should actually be contrasted with best of n. So if you want to satisfy a hard constraint, best of n can, roughly speaking, take like exponential in L number of function evaluations. And also, it doesn't even sample from the corrected tilted distribution in general. Okay, so this is some of the good results. Again, VGB, AR-VGB actually shares some of those results. But also another interesting thing about AR-VGB is that it's versatile. It not only does generation, it also does editing. What do I mean by that? Okay, you can generate out of nothing and reach the leaf node, and also the longer you run, the better rewards you're likely to get. But you can also start with a bad sequence, for example, a code with bug, and then you can start at the leaf. You run the same process, and then it'll actually repair the bug. It'll give you like higher rewards as you keep on running. So this editing / repair thing is actually a strong case where autoregressive is actually better than Any-Order AutoRegressive or diffusion, if you prefer, can be better than autoregressive. This is really like a more detailed version of what I showed earlier. Sorry, let me try again. So long sequence, there's some error, but you didn't realize until you are at a much later stage. So if you do like mask diffusion model, you directly edit the distant token. Like this token gets fixed. So in total, like you spend 4 steps, so 4 function evaluations, and you're done. But if you are doing like autoregressive, you have to work really hard backward. And even if you do like chain of thought that allows you to like go there directly, you still have to generate the tokens later on. So it's going to take a long time. We are almost done. So in the end, in the end, you get like 2 orders of magnitude more computes. I should have said that in this case, the terminal verifier is just a hard constraint that is like whether you match all the parentheses. But I don't want to give the impression that we can only do toy examples. We can generate like biomolecules, actually inorganic molecules using SMILE string, etc. Let me finish by saying, okay, so for example, in this situation, the base model actually has 0 accuracy. By doing backtracking, you can get 100% accuracy with fixed computational budget, which is not even big. And for like a generation of biomolecule base model, it's like 3% accuracy. By doing like VGB, MDM, you can get 60%, and then we have more tricks to actually give you like 90, whereas again, within fixed computational budget. And it really scales with inference time, etc. So. And also, you actually sample from the correct tilted distribution, whereas a lot of test time scaling methods actually don't. Okay, that's all I wanted to say. Thank you.
A couple quick questions for Molei.
What's the role of lambda in this?
Great question. Yeah. So lambda is a hyperparameter, and it basically, it encourages. So it's like how strongly remasking prefers high-value parents. So if your parents are very high valued already, and you use a large lambda, and then you remask more.
So is this related to momentum? Is this some momentum?
So lambda here is not related to momentum, but we did have a momentum version which I didn't talk about at all. It has more hyperparameters as well. Yes.
The process reward, do you estimate it with Monte Carlo?
Yes. Yeah. So we do like a Monte Carlo rollouts, and then we learn a process verifier. That's the most common situation. There are like rare situations where you can do better, but in general, it's something you have to learn. Yes, please.
The first part, how the analysis work to say lies on the ridge, like the analysis, how does it work?
Sorry, say it again, please.
In the first part, you say like the after generalization, it lies on the ridge, like the How does the analysis work?
How does the analysis work? So it's been. So we first conjectured that generation is related to ridge, and then we sort of bound the solution to the backward process, bound the distance between the solution to the backward process and the ridge. Yeah, I'm happy to say more.
Maybe let's take any other questions in the break in the interest of time. Let's thank Molei one more time. And we'll be back at 3:30, right? 3:30.